This will be a tutorial on breadth first search, including what it does, how it works, an image demonstration, pseudocode, and a running time description. We'll go through these points, but I don't expect you to understand how it works just from reading this. When we get to the image demonstration, it'll be much more clear. We're going to aggregate vertices into containers. These containers are going to represent levels. The starting element is going to be placed into its own container, L at 0, level 0 in other words, and we're going to insert into container L1, that's a new container, each unexplored vertex in the graph that is connected by an edge to the vertex in L at 0. So there's a bunch of edges leading from L at 0, we'll assume, and they're going to lead to other vertices. Those vertices are going into container L at 1. Then similarly, we'll insert into container L2 each unexplored vertex in the graph connected by an edge to any vertex in L1. There's presumably some vertices in L1. They have some edges presumably that lead to other vertices. All of those new vertices will be placed in container L2, meaning level 2. We'll continue this process until there are no unexplored vertices left. Here's an image demonstration. So you can see that these are vertices, red circles, edges are yellow lines, and these represent levels. These little, I circled these here in purple. So this is the start vertex. We put it into level 0 to start. It's going to have some edges coming off from it. And so these are going to lead to opposite vertices. Here's vertex 1, opposite of the start vertex, another vertex opposite the start vertex, and a third one. They're all going into the next level, level 1. And so where do these lead? This one leads here, this vertex leads here and here, this vertex leads here. So these are the 3 vertices that are led to from the previous vertices. So they're going in their own level, and similarly we'll create level 3 like so. Here's pseudocode. So breadth first search method is going to accept a graph G and a vertex S. So we will initialize I at 0. We'll create a new container, L at I. That's going to be L at 0. We will insert S, our start vertex, into L at I, which is L at 0. While L at I is not empty, L at 0 is not empty because we just put S into it, we'll create a new container, Li plus 1. So that's for the next level, right? For each vertex v in L at I, so for each vertex in L at 0, that's this one vertex. Now for each edge e in g.incident edges v, so for each edge that's incident to or incident on v, this edge is incident on v, that just means it's connected to it. This edge is incident on v, this is v, right, the starting vertex. This edge is incident on, these 3 edges. So for each edge, incident on v, if e is unexplored, they're all unexplored, we haven't done anything yet, w is going to be assigned to g.opposite ve, that's a vertex. This is the graph, and it's opposite from our vertex v, our starting vertex, along edge e. That's w. This is going to be w, this is going to be w, this is going to be w. Opposite across e, with each iteration of the for loop. Now, if that vertex is unexplored, haven't been there yet, we're going to insert the vertex into li plus 1. So this will be L1, level 1, as you see we've done here. Then we'll label E as a discovery edge because that edge led us to a previously unexplored vertex. Else, if it's already been explored, we'll label E as a cross edge. And then we will increment I. So by the time we're done this, we'll have an L4, right? And our while loop says while L at I is not empty, well, there will be nothing to add to L at 4, so it will be empty. So we'll terminate. That's how this method will terminate. So the running time is very similar to the depth first search running time. We can explore each edge at most twice, once from each vertex. Right? You can go this way or you can go this way. That's the only way you're going to get to this edge, through one of those endpoints. We'll explore each vertex at most degree v times, where the degree of a vertex v is the number of edges which have vertex v as an endpoint. In other words, in the worst case, the number of times we traverse a vertex is the number of edges incident on that vertex. So how many times can we get to this vertex? We can only go in 2 ways. This vertex, hey, maybe we can come in 3 different ways, right? So that's the degree. The degree of that vertex would have been 3. So therefore, the running time of breadth first search is, this is an upper bound, so it's order v plus e, where v is the number of vertices in the graph, and e is the number of edges. So if you have any questions on this, you can ask them at leafy.io, and you can find some help there.